when strontium has a chemical reaction with titanium and oxygen, it makes strontium titanate, which can outsparkle even diamond because it has a high refractive index. What's that, my love? What's a chemical reaction? That's a really good question, and I think the Year 7s would like to explore that with us as well. That's right. So, you know that you need lots of energy, don't you? Yeah? Your body has to undergo a chemical reaction to do that. So, Year 7, what happens inside your body is your body breaks down food and oxygen, and that chemical reaction releases energy in the form of heat, and we can use that energy to do all sorts of things like think and move. And that's why after you go for a run, you feel really hot, because you've had to release lots of energy. You've had to do loads and loads of these respiration reactions. William, stop that, darling, thank you. And those respiration reactions release heat. So sometimes a chemical reaction which breaks down molecules and rearranges the atoms and makes new ones can give off heat. And that's how we can know a chemical reaction's taking place. Chemical reactions occur when molecules are broken apart and reform into new molecules. And we can write it like this: reactants make products. That arrow here means that something new has been made. It is not equal, otherwise I would have put an equals sign. They have made something new. The reactants have made the products. So in this case, my reactants, my chemicals that are going to react, are hydrogen and chlorine. What happens is we break them apart. We break the bonds between the molecules. And then they rejoin and make something new. In this case, we've made hydrogen chloride. Our product, we have produced hydrogen chloride or hydrochloric acid. Okay? So how do we know when a chemical reaction is taking place? Well, as I said earlier, it could be that we give off heat. So a change in temperature might mean that things get warmer, or it might mean that they get colder. It just means the temperature has changed. In this case, things are getting warmer. So we have our respiration equation here, which is glucose and oxygen make carbon dioxide and water. Carbon dioxide is a gas, oxygen's a gas, water's a liquid, and glucose is a solid. They are not equal, are they? You can see that they are different chemicals and they would react in different ways. I've put the chemical equation underneath, but it is what we would say unbalanced, which means we don't have the same number of atoms on each side. Don't worry too much about balancing equations yet. We will deal with that later. So yeah, changes in temperature mean that a reaction's happening. There are other things that can happen as well. For example, a smell could be made. Now, most of the smells made are pretty yucky, but I've come up with a reaction that you can do at home that will involve making a nice smell, and it is this. What we're going to do is we're going to take butter or margarine or oil, it doesn't matter, sugar, eggs and flour, and we're going to make something that gives off a smell while the reaction is happening. And what we're making is cake. So come on, into the kitchen, let's do our first chemical reaction. And because we're doing science experiments, I expect all long hair to be tied back. We're wearing safety glasses because we have them. In your case, don't worry too much for this experiment. Okay, if you have something that you can use to wear for the next experiment, though, that would be great. So, we've got a bowl and a wooden spoon. what we're going to add first is the butter and the sugar. And then we stir it all up. As you can see, my lab assistant very ably assisting me here, until it's all creamed together and it looks like this. Next step is to add the eggs one at a time. 1 egg and mix it in. 2 eggs and mix it in. And 3 eggs and mix it in. And finally, we're going to add the self-raising flour and mix it in really slowly at first, because otherwise the flour will sploosh out everywhere. Okay, and you end up with this, which is cake mixture. This isn't cake in itself yet. The reaction to make cake needs energy, and we put that energy in the form of heat. Okay, so, but before we do that, this is a mixture. Now, we missed out a bit on mixtures yesterday. Mixtures haven't been chemically joined together. You can separate them. So can I separate this cake mixture into sugar and flour and butter and eggs? What do you think? Well, not when I'm this size, you're right. But what we can do is this. Shrink me down to the size of an atom. Have you finished? Right, and now we're going to do it again. And you are literally going to film me for a... Here I am, the size of an atom inside the cake mix. And this is what I can do. I can reach out and grab some of our butter and some of our sugar molecules. These molecules haven't chemically joined together. They're still separate. And I can separate them all. But being this size and the cake mix being this big, it's going to take a long time. And I just have to mix them all together again. So what I'm going to do is put these back where I found them. You went up there. And then we'll go back and make me big again. Excellent. I'm back to normal size with no misadventures as well. Andy could learn something from me, couldn't he? So we're going to take our cake mix, we're going to make sure it's mixed up, because I did move some of those molecules around, and then we're going to add it to a cake tin like this. We want as much of the mixture as possible to go in here, because we want it all to react and turn into yummy cake, don't we? Okay. Okay, so that's all the mixture into the cake pan. Mine's non-stick. Your parents may tell you that you needed to grease the pan beforehand. So once it's all nicely smoothed over, we're going to put it into a preheated oven. But be careful doing this, because ovens are hot, hot, hot. And then we need to leave it for half an hour until it's all reacted. Hopefully you should be smelling it long before then, so that we can understand that chemical reactions can sometimes give off a scent. Okay, so while we're here, chemical reactions can also set things on fire. So as you can see, what I'm setting on fire here is the gas which comes into my house, methane gas. It's been set on fire and it is burning. So chemical reactions can also involve fire. This is my favourite, and actually I'm a little bit disappointed, because it's normally at this point when I get to do the methane bubbles experiment. I love methane bubbles. It's where I get a big washing up tub with washing up liquid and a bit of water in, and I put methane, I bubble it through there, you get all these lovely washing up bubbles full of methane, and I set the thing on fire and it goes whoosh, and I love it, and I can't do it. We don't have the equipment here at home, and even if we did, it wouldn't be safe to play around with it because it's not, yeah, I mean, I love blowing stuff up, but only when it's safe. I could end up with a gas leak and blowing up the whole house, which wouldn't be safe. It'd be fun, but it wouldn't be safe, so I'm not going to do it, unfortunately. So anyway, let's go write this down. We can also get fire. Okay, so here we go. We can catch things on fire. We've got methane, and it reacted with the oxygen in the air, and it makes carbon dioxide and water, similar to our respiration equation up there. And if you remember from last lesson, methane is CH4, oxygen's O2, carbon dioxide CO2, and water's H2O. So you may remember these molecules from yesterday's lesson. Methane, CH4, and oxygen, O2. I've got two of them for a reason. Okay, so what happens in a chemical reaction is all the bonds break apart. And we're left with a jumble of atoms, which then reform like this to make carbon dioxide and water. One carbon dioxide and two waters. You will notice that the amount of atoms I had at the beginning is exactly the same as the amount of atoms I had at the end. Okay, that's what you need for a chemical equation, the same amount of atoms at the beginning and the end with none left over. So if we are going to write this properly, we had one methane molecule and two oxygen molecules, which made one carbon dioxide molecule and two water molecules. So I'll just put a 2 there in front of the water. There will be lots and lots of practice for balancing equations over the years. I just wanted to show you that's what you need to do. I'm not going to push balancing on you at the moment because it's a little bit advanced. However, some of you will have noticed that the atoms on each side weren't adding up and would like to know more. It is very, very difficult to make a video for a whole group of people with lots of different ranges and mathematical and scientific interests, so that, you know, everyone's starting from a different place. So if you don't see why that has to happen, don't worry, it will be done again later. If you were wondering why the atoms on each side weren't matching up, they now match up. So hopefully there's something for everyone in there. So another chemical reaction that can happen, or a sign of a chemical reaction, is a change in colour. And we see this when we use green copper carbonate and we add in sulfuric acid, which is colourless. Please notice that all my reactants are on the left of the arrow, even though it meant using 2 lines. And we have made blue copper sulfate, colourless water, and carbon dioxide, which is a colourless gas. Those are the chemical symbols, chemical formulae for the various chemicals as well. Another point when writing chemical equations, as I said, all the products on the left of the arrow, all the products on the right of the arrow, all the reactants on the left. Reactants are going to react to produce the products, and we keep them to each side. I know that's not how you would be told how to write in an English lesson, but in a chemistry lesson, all your reactants on the left of the arrow, all your products on the right, please. I just don't want you losing marks in 5 years' time because no one told you this in year 7 and it was just assumed that you knew in year 8 and assumed you knew in year 9, and then you lose your marks in your GCSE because no one tells you. Yeah, so there we go. Copper carbonate and sulfuric acid make copper sulfate, water, and carbon dioxide. Thinking of carbon dioxide, giving off bubbles is another really good sign that a chemical reaction is happening. So this one's a bit messy, which is why we have relocated outside. I've put a little bit of washing up liquid inside my volcano. If you don't have a volcano, any small cup will suffice for this. Champagne glasses are really good because they've got about the right shape and size. And to that, we're going to add some vinegar. Well done, Theodore. Okay, so, William, leave that in there, please. Okay, so, Theodore, you're nice and safe with your glasses on. You've got a big spoon, haven't you? What I would like you to do is, can you please put this bicarbonate of soda, if you haven't got bicarbonate of soda, baking powder will work, but not as well. Come away from the scooter so you don't fall over. Oh, I'll move the scooter, good idea. Can you please tip the bicarb into the volcano and I'll remove the funnel once you've done that. Oh, it's not going in, is it? There we go. Give it a bit of a mix to start the reaction going. And no, don't put your head over it because here we go. Nice, messy, lots and lots of bubbles of carbon dioxide coming out of my volcano. Lots of bubbles, that's right, William. Okay, let's take a look at what the reaction for that actually is. So here we go. Bubbles or gas given off. The proper chemistry term for it is effervescence. But again, that's one of the things you don't have to worry about. Bubbles, fizzing, gas, anything like that is fine. And the reaction is ethanoic acid and sodium bicarbonate. Ethanoic acid is that lovely vinegary smell that you probably all recognise as being vinegar. Makes sodium ethanoate and water and carbon dioxide. Okay, one last one, and unfortunately this is another one that I can't do because I can't get the chemicals at home, so I'll just have to tell you about it. And that's the reaction that makes a sound. So if you make hydrogen gas, which I'm sure you will be able to do in the lab next year because this is a fantastic experiment, and you light the hydrogen gas, so you make it react with oxygen, you set fire to it, you get this amazing squeaky pop sound as it makes water. So hydrogen and oxygen react to make water with, because we're doing it in the lab with small amounts of hydrogen, it makes a squeaky pop. If you do it outside the lab, you get a great big boom, which is an amazing sound. And I promise you there will be time to do this when we are back at school, just not right now. Some of you also may have spotted that this reaction, the chemical equation for it, isn't balanced. If you fancy having a go at it, have a go at it and send it to your teacher at the end of the lesson. You do have a worksheet about spotting chemical and physical reactions to do. So if you don't want to have a go, don't worry. There will be a way of showing your teacher that you've accessed the lesson. Okay, so my cake has finished cooking and I've taken it out of the oven and put it on a plate. It's still a little bit warm, but it's not too bad. So the next thing is, this is a plain cake. I'm going to want to do a topping. Now you heard me say physical reactions. All I've done so far is talk about chemical reactions. What's a physical reaction? Well, you've done about changes of state, yeah? You remember that? A physical reaction is where we are changing the state of something, but we're not actually changing what it is. So a physical reaction might be, for example, water. I've got some water here. If I froze it into ice, that would be a physical reaction. It's changed, but the chemistry of it hasn't changed. Same as when I heat it up. Okay, light a fire underneath it, heat it up. It's going to turn into water vapour and leave as it gets hot. But again, that's a physical change, because if I cool it down, I will have water back again. Here's another physical change. If you don't have a bain-marie, don't worry. You can do the same effect by putting one pan inside the other. And what we're going to do now is I've got a bar of chocolate and I'm going to break it all up. It's easier to do it inside the wrapper, so it makes less mess, but if you want to do it outside the wrapper, that is completely up to you. And what we do is we put the chocolate inside the bain-marie, like this, and the hot water will melt it. Okay, we can't heat chocolate directly with a flame underneath it, because then it burns and it turns horrible. So we're just going to wait a couple of minutes for this all to melt. Okay, so my chocolate has now melted, and what I'm going to do is I'm going to take it, just wipe the bottom of the thing, of the bain-marie off, and very slowly pour it over the cake. I'm doing it in a nice spiral pattern to spread all the chocolate out, and also to prevent it from going too far off the edge. One sec, just remove that. It's not going to prevent it from doing it entirely. There we go, and this is again quite volcano-like, isn't it? Like all the lava, pyroclastic flow down from the volcano. Okay, so once you've got all your chocolate out, we need to leave that to cool. We need to get our liquid chocolate back into solid chocolate. And once that's happened, I've got my teapot ready with the tea bags in. I can take my boiling water, pour it into the teapot, and go back outside to enjoy tea and cake. Okay, so to recap, chemical reactions is where the chemicals actually change. The bonds are broken and new molecules have been produced or formed. Physical reaction, as soon as the temperature changes, I get my original thing back. So my liquid chocolate's going to turn back into solid chocolate, but I can't turn my cake back into sugar, flour, eggs and butter, because I've cooked it, reacted it, and it's gone. Hope you've enjoyed that. Hope you were able to do some of the reactions as well, and I shall see you for another lesson very soon. Bye.